Many of my regular viewers will have seen my robot dog development over the last few years. The last working robot dog I built is openDog version 2, which works okay. During development, I discovered that having back-drivable gear trains is very important. This allows natural spring in the legs, but also allows this springiness to be controlled in real time by altering the way the motor is driven. However, there's quite a lot of torque required, as the drive reductions ideally need to be less than 10:1. openDog version 2 uses belt reductions because that was the simplest thing I could come up with at the time, but there are only 5:1 reductions due to the physical space required for the belt and pulleys. Since then, I've been thinking about a more compact gearbox solution. I really like to keep the hardware as open and accessible as possible, so it would be ideal if the solution was 3D printable. The robot's feet hit the ground quite hard and it can move quite fast, so I'm pretty sure that 3D printed planetary gearboxes with only a 10:1 reduction wouldn't last long. So, a while ago I started development on cycloidal drive gearboxes, which use a set of much chunkier cycloidal discs. I've done quite a bit of testing with these reductions, including having one push me on a skateboard for a few miles with no visible wear, and it was all printed in PLA. Last time I built a test robot dog leg using 2 cycloidal drives, and this time we're going to build 12 of them and put the entire mechanical assembly for openDog version 3 together. A lot of parts have been printed, and as usual, thanks to 3D Fuel for the filament for this project and lots of other projects, so check out my channel for more 3D printing projects and check out 3dfuel.com. When I built the test leg, I put nylon bushings in all of the pegs in the cycloidal drive, and it kind of ran okay. It wasn't quite as good as the previous test cycloidal drive though, which I used lots of bearings in, and you can see that that one runs much smoother. So we're going to go back to bearings for this design. That does however mean that I need 384 bearings for the middle of the drive and the surrounding pins, but I managed to buy all of these as about 400 on AliExpress for $70 the lot. I also bought the big bearings for the back and front of the drive and the medium-sized bearings that go on the cam assembly. That also meant I had to cut 132 pieces of 4mm steel to put them on, and yes, I did that with a 3D printed jig, and then I deburred the end of every single one, or at least both ends, with a Dremel. And of course I need 12 motors, so I've got 12 Eagle Power LA8308 motors, which are in fact a 9225 can size. Everyone needs the central pin chopping off though, and I did that with a Dremel cut-off disc, and I masked off the rest of the motors to stop bits going inside. And all of those get mounted into the 3D printed motor housings. And the reason I chopped the middle pin off as before is because I need to mount directly on top of that with the cam, which has a captive nut in the bottom. I've mounted the large bearings in the top and bottom of the cycloidal drive casings, and the motor screws onto the back of that. I've also mounted the output shaft bottom, which fits into the bottom bearing, and that spins independently from the motor cams. So that's the first set of bearings and the first cycloidal discs fitted, and every bearing has a washer underneath that brings it up to the right height, and I've used nylon washers for this. If I move the mechanism slowly, you can see that those bearings are really going to help, because the cycloidal disc doesn't roll over them at all, it actually scrapes past them, and that's probably why these gearboxes run smoother with bearings in. So we're up to the second stage. I've got a 5mm nylon spacer in between the two stages of bearings. And that's the second cycloidal disc. I put another washer on top before we put the top casing on, but everything seems to run pretty well. So that's my top casing, and you'll have noticed that this is actually a double cycloidal drive, and that's because for this part of the design I needed to fit them so closely they were actually touching. There's a cap on the cam, and that has an M4 socket cap bolt that goes all the way through into that captive nylon lock nut we put in at the beginning. And that allows another bearing to be mounted on top that holds that cam centrally while allowing the output to rotate in the opposite direction. So that's not running quite as smoothly as the original one with bearings, although that one didn't actually have the right shaped cycloidal disc. It was kind of a made up wobbly shape, and that one does run a lot smoother. However, it does have lots of backlash in due to the poorly shaped cycloidal disc. So that's really not that good at all, because there's a large gap in the gears. The new one though has hardly any backlash. I'm really happy with how that's come out with the proper shaped cycloidal discs. So even though it doesn't run as smoothly, there's much less backlash, so I think it's going to be pretty good. And I've been making 2 of these double cycloidal drive units, which makes up the first 4 cycloidal drives for the robot dog. They've got these pieces on, and those attach to the next cycloidal drives, so here's another 4 cycloidal drives, and these ones look slightly different. Basically, there's a gap in each end for a pivot point to be attached. And that of course attaches to the first cycloidal drives to make a perpendicular axis. 2 of those fit to each one, and that allows the legs of the dog to move sideways. Before we attach anything to those axes, we're going to put some carbon fibre tubes in that make up the body of the dog. So the first 2 units just slot in, and those are a really tight fit. I've also made a stand so that I can work on it, so we can pop the whole thing in. And the carbon fibre tubes just align into hooks that I've put at each end so we can easily lift it out. With that in place, I've now fitted the next axis, and that is going to make up the shoulder joint for the leg. You'll have noticed the extra pivot point at the end on the other end of it where it's not attached to the previous cycloidal drive, and that's so that can be mounted into another piece to support it. I'm using thin wall bearings, and these are actually the same bearings I used throughout openDog version 2, despite them looking quite puny. These are fitted into a 3D printed plug though, so I can always change that easily without changing the whole end piece. And those are a really tight fit. I have to use a rubber mallet to fit that on and get everything aligned. But once the back and front are fitted, we can see those move smoothly, and they should be well supported on those 2 sets of bearings. I've also put these holes in, which will allow me to put tie bars in if the parts slip off the carbon fibre tubes. And of course, stuck onto those axes are another 4 cycloidal drives, which make up the knee drive. Those have a pulley and a little cap that fits onto a bearing we've already placed in the leg. And the lower leg has another pulley on. And the lower leg is made out of a 3D print, a carbon fibre tube, and a TPU printed foot, which is very similar to openDog version 2. And that should absorb quite a lot of impact when it hits the ground. There's a 9mm wide HTD belt, which is a 5mm pitch, and it fits between those 2 pulleys. And that's a 1:1 ratio, so all of the axes move at the same speed. We've got a place there to put 2 idlers to tension the belt. I already fitted a bearing in the upper half of the leg, which the knob on that pulley fits into, and that will stop the mechanism skewing and the belt skipping. The lower legs are mounted on skate size bearings of an 8mm internal diameter, and I've fitted all of the idlers now, which has made the belt very tight, so we seem to have a really good range of motion. If the belts stretch, we'll just make them tighter by increasing the idler size, which is of course just 3D printed and mounted on 2 6mm internal bearings, so that'll be very easy to rectify. There is one small issue, which is if the leg moves out too much, then it hits the carbon fibre tube at the top, and it's even worse when the leg is facing forward or backwards and that diagonal piece hits it. However, that's actually quite a lot of motion, so for stepping sideways, it's never going to move its leg that far, and openDog version 2 only moves backwards and forwards about 50mm. If we turn the legs, they will fold up completely though for transport, which means the whole thing could go in a flight case, just like Spot Mini. So I'm pretty happy with that so far. It's pretty solid feeling. It does weigh slightly more than openDog 2 did. It weighs 20 kilograms as it is now, and that's quite a bit heavier than openDog 2 due to the extra bearings that we've got in all of these cycloidal drives, both the big ones in the back and front and the 3 in the middle, and of course all the small ones inside, although that didn't make much mass difference from when I tried the test and put nylon bushings in. So it's mainly the bigger bearings that have caused that extra mass, times 12 of course, because there's 12 axes. The battery from openDog 2 is this one though, which is just a drone battery, and we're actually going to draw less current from all of this, so that should still be sufficient, or we could get 2 in and double the battery life, plus. So obviously we still need to see if this works. I've still got to put electronics in. It's going to have 6 O drives in again and a microcontroller of some sort, but that's pretty much it. So it'll probably end up about 25 kilograms. I think for comparison, Spot Mini from Boston Dynamics weighs about 30 kilograms, and hopefully this is going to work better than openDog version 2, but not quite as well as Spot Mini. So I'm going to publish this as open source, and all the CAD and code will be available, but I'm not going to do it just yet, as usual, because I really want to power this up and check that it does actually work before I publish it, and there's quite a way to go yet. So don't forget to subscribe and like the video if you liked it, and check back for more updates, which will be coming soon. If you want to support me through Patreon or YouTube channel membership, then those links are in the description to this video, and patrons and YouTube channel members can get access to all the videos up to a week early, and sneak peeks and pictures of what's coming up. Alright, that's all for now.